Welcome back. What we want to do in this video is find the average value of a function f of two variables x and y on a rectangular region R. All right, so how do we do that? Well, let's say here we have the rectangle R, where the rectangle is determined by the interval from a to b along the x-axis and interval from c to d along the y-axis. We are going to pick a partition P of this rectangle. We are going to divide the rectangle into m vertical strips, where we are dividing the rectangle at the points x0, x1, x2 up to xm on the x-axis, and we are dividing the rectangle into n horizontal strips as well, and we are dividing the rectangle horizontally at the points y0, y1, y2, yn on the y-axis. So again, we are dividing the rectangle R into m vertical strips and n horizontal strips here. So together we get m times n sub-rectangles here. We are going to assume that the sub-rectangles, they have these sub-rectangles have the same area. So let's say delta A is the area of each of these sub-rectangles. So the area of the ijth sub-rectangle is equal to delta A for any I and j. Now the area of area of each of these sub-rectangles would be equal to the area of the entire rectangle R divided by the number of sub-rectangles. And from this equation we can say that the number of sub-rectangles mn is equal to the area of the entire rectangle R divided by the area of one sub-rectangle. Okay, so how would we approximate the average value of f on this rectangle? Well, let's pick a test point in each of these sub-rectangles. So we have m times n test points here. We evaluate f at each of these test points, and then we take their sum. So this sum right here is the sum of the values of f at the test points, and we divide this sum by the number of test points mn, and that is an approximation of the average value of f on this rectangle. Now 1 over mn, that's the same as, since this mn is a over delta a, 1 over mn would be delta a over a, and we're going to put the delta a inside of the summation, and if we do that we get 1 over a, and then this summation I going from 1 to m, j going from 1 to n, f of xij star yij star multiplied by delta a. So it makes sense to define the average value of f to be 1 over a times the limit as mn goes to infinity of this sum. And obviously it makes sense to define it this way because our approximation of the average value would get better and better if m and n gets bigger and bigger. So, but recall that this limit is exactly the definition of the double integral of f over the rectangle R. So the average value of f is equal to the double integral of f over R divided by the area of R. Okay, so let's do an example. Let's say that I have the function f of xy which is equal to 16 minus x squared minus 2y squared. And let's let R be the rectangle determined by the interval from 0 to 2 along the x-axis and the interval from 0 to 2 along the y-axis. What's the average value of f on this rectangle? Well, the average value of f would be 1 over the area of R multiplied by the double integral of the function f over R. Now, the area of R is 4 because this is a rectangle with length is equal to 2 and width is equal to 2. So the area of R is 4, so we get 1 over 4, and then by Fubini's theorem we can write the double integral as an iterated integral where we have integral from 0 to 2, 16 minus x squared minus 2y squared dy dx. So that is, we are the inner integral here is with respect to y, and then once we compute this inner integral, we are going to get a function of x only, and then we have to integrate that with respect to x from 0 to 2. And so if we do that, we're going to get 48. So we get 48 divided by 4, which is 12. I'm not showing the steps for evaluating this iterated integral because we have done this previously.